Okay, so now we've hit some of the most important parts of studying kinematics, and that's actually these equations. Okay, so another way to model. So we've really spoken about three ways: the descriptions, the graphing, and now we're going to talk about another way, which is the equations. So now this is a set of formulas that are known as the kinematics equations or motion equations, and they all assume that the acceleration is constant. With this being an algebra-based class, this is very important that the acceleration is constant. If you take physics C, then the acceleration at times will not be constant. But that's just for them, for College Board to be able to use calculus. Okay. Now, what you'll see, there are 5 variables that are present in this set of equations. Now, each of the formulas will contain 4 of the 5 variables. And so the variables are going to be displacement, which is represented by delta x, which in the long run is x minus x0 or xf minus xi. You will have initial velocity, which is represented by v0 or vi. You'll have final velocity. Now these are 2 separate variables in the equations, which will be represented by v. Then you have acceleration, which is a, and then you have the final one, which is time. Okay, so you'll see there's 5 equations, or excuse me, 5 variables, and each of these equations will have 4 of the 5. And that'll lead us to the problem-solving strategy, which you'll see in a second, but is to write down your given values, write down these 5 values, and then determine what's missing and what's there. Okay. So what we're going to do in this chart is we're gonna break it down into what the equation is, and we like to call it cake, right? And as in constant acceleration kinematics equation, it's just an acronym, right? So C-A-K-E. As in these equations are a piece of cake, right? So that's what this really means. You'll see though that we do break up the displacement into 3 columns, or it's xi, which is our xo, xf, or x, and then delta x. And then you've got initial velocity, final velocity, acceleration, and time. And then the last column is just what happens when acceleration is equal to 0, or when we have constant velocity. Because technically acceleration, if it is 0, is a constant acceleration, but it's just constantly 0. Okay? So the first equation we'll look at is v equals vo plus at. And what we'll do is the variables that are missing, we'll put a frowny face, which just says it's missing and we're not asked to look for it at all. Okay? When you do the problem solving strategy, if it is missing but you're asked to look for it, you're going to put a question mark. Okay? But if it's missing and not asked for it at all, you're going to put a frowny face, and that's going to help you identify the equation to use. So in the equation, you can see we do not have xi or xf, which means we do not have displacement, but we have the other 4. Okay? And if I plug in a is equal to 0, well, this just kind of reiterates the idea that constant velocity means that it doesn't change. The second equation, v equals vo squared plus 2a delta x. So we would have xi, xf, we would have delta x then. We have initial velocity, we have final velocity, we have acceleration, but we don't have time. I like to call this equation the equation that time forgot. And so if we now plug in 0 for acceleration, you'll see that we get this v squared equals vo squared. But that, again, if we take the square root of both sides, it just reiterates that if you have no acceleration, then your velocity remains constant. Okay. The next equation is probably the most important one, and this is what it boils down to is the equation of a position versus time graph. Okay. Now I am going to set it equal to delta x, but you could expand this to be x minus x0 and then solve it for x, which you get a true equation for a graph. But so that means we have xi, xf, we have x, or that means we have delta x. We have initial velocity, but we're missing final velocity, and we have acceleration, and we have time. So if we plug in 0 for the acceleration, we end up with an equation that looks like this. But if we expand this, we end up with x equals x0 plus VOT. And what this boils down to, this is sometimes referred to as the position equation. Okay, that's because it solves for the position at any time when knowing the initial velocity and the time. And then the last one, it's the only equation that does not have acceleration in it, which means if your acceleration is constant, that means technically you can find the average velocity by just simply doing VO plus VA plus V over 2. So it's set equal for displacement, which means we have the first three. We have VI, we have VF, or V and VO. We're missing a, and we have T. And again, since this has no acceleration in it anyways, it's really not a help to us. Okay, it doesn't really show constant velocity or anything like that. It doesn't show, in the long run, it kind of shows just another version of this formula, but it's not the initial velocity, it's the average velocity, and that's what that little bar symbol stands for. Okay, and so now let's look at the strategy. I will highlight just some key things here. When doing AP test, this first bullet point here is the important one, right? So the AP test is a game. You're trying to accumulate points to get into the score that you want, right? And where do your points come from when you do the free response section? It's your work, okay? So your first step, you're going to write down the variables and their values. If the variable is missing completely, not given or not what is being solved for, that's where our frowning face comes into play. All right, that's why we put that in there. So be sure, then you need to be sure to identify what you're looking for with the question mark. Step 2 is to write down the equation based on step 1. So you're going to look for the equation that has those variables that you know that you have, plus the one you're looking for, and missing the frowning face, and then write that down. Okay. The step 3 is to actually do the algebra, and this is important. This is a step that students don't want to do because they want to just plug in numbers, but sometimes the AP test actually has you solve for expressions and not actual values. So that step there is necessary. Step 4 is almost optional, especially if it's a question that just says, hey, what is this in terms of this? What is this variable in terms of this variable, and that variable? Okay, so that's why step 3 is just as important as everything else. So that my recommendation is to do step 3 definitely before you do step 4. Okay, plus it just helps you make sure that you have the right the equation solved the right way, and you're plugging in positives and negatives. Okay, so let's do just a couple examples to see how this strategy works. All right, so we've got the M40 Marine Corps standard issue sniper rifle's barrel length of 61 centimeters. So as we go along, that will be our displacement. Now we need to convert that to meters. So I'll do that right away. We're going to divide this number here by 100. It has a bullet muzzle speed of 77 meters per second. So before we pull the trigger, it's moving at 0 meters per second. Then we pull the trigger, and then it's moving at 777 meters per second. And now we're going to find the acceleration experienced by the bullet. Okay, and then express this in number of G's, right? So they want to know how many G's this is equal to, right? G's is just, it's like G-force. They're talking about how much it's being accelerated compared to acceleration due to gravity, which they tell you here is equal to 9.8 meters per second squared. On the AP test, if it's not given to you, you can actually use 10. And notice, so we'll write down our fifth variable, which is time. Okay. It's not asked for, so that's our variable that we don't have to worry about. Okay. So we're looking for the equation that has delta x, has displacement, has initial velocity, final velocity, and acceleration, and no time. And so if you remember, it's the one v squared equals VO squared plus 2a delta x. Okay. And now we're just going to do the algebra to get a by itself. And this is not necessarily hard algebra, but this is one where students just kind of want to like divide everything by 2 delta x. See the a right there. But your first step is to actually get rid of the VO squared. So if you remember from math class, you got PEMDAS, right? So when you evaluate, you go this way, you go PEMDAS, evaluate, but when you solve, you go the other way, right? So you have to tackle the addition and subtraction first, then you tackle everything else. So in actuality, the first step is I need to subtract this VO squared over. In actuality, you can, one step that's easier, especially, okay, one thing you can do is VO squared is 0. Oh, sorry, I just erased all that stuff that I just wrote. So VO squared, right, is 0. So we can get rid of it, leaving just us the 2a delta x. Okay, so then we just solve simply for a. So a is going to be v squared over 2 delta x. Right, so this should be a positive answer. Doesn't make sense because we're going to call the starting point where all this happens, that's going to be our 0 point, right? And so that's going to be also be our initial position is also going to be 0. So we're going to accelerate this in the positive direction. So we're going to plug in values, 777 squared over 2 times 0.61. Now, because you're dividing a big number by a small number, you should expect a big number in return. And it should be considerably bigger because when you square something to the 100, it's going to be in a 10 to 10,000 to 100,000 range. So if I do that, I'm going to get the big number. So I'm going to write this in scientific notation. So 4.95 times 10 to the 5th meters per second squared. Okay. But one thing to know, it does, so we found the acceleration, that would be a positive, but they also want us to express it in number of g's. So basically this is just now just a conversion factor. So we're going to say that 1 g is 9.8 meters per second squared. All right, so that would go the way, that would go away. And so your final answer ends up being 5.05 times 10 to the 4th g. Right, so that's the acceleration in terms of g's. So these are your two answers: 4.95 times 10 to the 5th meters per second squared, and then 5.05 times 10 to the 4th g's. Okay. So now let's do another one. So here we have a question that says the car leaves a skid mark of 70 meters while coming to a full stop, assuming that a constant negative acceleration. What was the car's initial speed? Okay. So with this one, there is a piece of missing information in the problem. I forgot to give what is that constant acceleration. So we're just going to say it's negative 3 meters per second squared. If they don't give it, if they say an acceleration of 3 meters per second squared, you're going to know that it's coming to a stop. So this has to be negative. Okay. So there are two questions here. I'm going to split this into two separate parts. So we have, for the first part, we have how far it took to stop, which was 70 meters. We also have the acceleration, which is negative 3 meters per second squared. Again, I had to write that one in. That's why I put it over here to the side. We know the final velocity, right, is 0 meters per second, and we know the initial, or we're looking for the initial velocity. And our frowning face, the one that we don't have, we don't worry about, is the time. Okay. So again, we're going to use that same equation we used in the previous question. But now instead of solving this for A, we're going to solve it for VO squared. Okay. But we can do a little bit of simplifying before, so we can call that 0. And then what we're going to do is we're going to subtract over the 2a delta x. Now again, this is where students will just, where you guys will just want to plug in numbers, forgetting that there is one extra step here, because note that this equation is equal to v squared, or VO squared, so we got to take the square root. So it's going to be VO squared is the square root of negative 2a delta x. Don't let that negative side under the square root scare you, because remember, your acceleration is 0, or excuse me, it's negative. So we're going to plug in the values. So we're going to say negative 2 times negative 3 times 70, and that'll give us the initial velocity. So square root of 2 times 3 times 70, and so that'll give us an initial velocity of 20.5 meters per second. And since it is looking for, this is looking for speed, not a velocity, so with it being for speed, we don't care about that plus sign. Okay, and now we go to the other side. You can redo all this, right? And so now we have, for the second part, we're looking for time, but note that we have really all of the variables now. So they're all kind of claimed, right? So we have delta x, we have a. Now, I'm going to leave the v blank for real quick, right? I just want to point something out. Let's say that this answer was wrong. Let's say 20.5 was wrong. That means that we can actually technically put our frowny face with the VO. You could use that 20.5, but if this answer is wrong, why make the assumption that this is correct when you're just going to put a wrong answer into and get another wrong answer? So let's just do it without. Let's just say that VO, we'll treat it separate and leave VO out of the whole process. Okay, so here, so we're missing, we want the one equation that does not have initial velocity in it, which is difficult because they, if I scroll back up, note that you'll see that one variable that exists in all of them is initial velocity. So we actually do need to go back to that first part for that answer. Okay, so some questions you don't have to use it, but here we will use it. Right, like if this is a reverse question, right? If we had time first, okay. In fact, you couldn't solve for time without the initial velocity. Okay, so now we just have we can pick whichever equation we want. Let's use a simple one. Let's use the first one, that v equals VO plus AT. This is simple algebra. Why make it more difficult than it already is? So we're going to solve it for t, right? So again, we need to subtract this VO over, so we're going to get v minus VO, and then we're going to divide it by a. But again, v is 0. You could have made that simplification here. So t is just going to be simply negative VO, or excuse me, negative VO over a. So it's going to be negative 20.5 divided by negative 3. And I mean, if you do a little bit of estimating, it's about 7, because it's roughly 21 divided by 3. But you're going to find that the answer will be 6.83 seconds. So that's how long it would take. I love this question because a lot of you guys are teenage drivers, right? And this is actually, what happens, if there's an accident, there's a job called accident reconstruction, and they come out and they do these kind of calculations. So they're using the physics in their job. And guess what? They're police officers. They're not physicists, okay? All right, so let's go. So here are a couple more questions. Okay, again, if we're in class, you guys will be doing this practice on your own, and I'll be walking around. Okay, so here we go. We got a 2013 Ferrari California's quarter-mile time, which is the time to drive a quarter mile or 402 meters starting from rest. Now, this is a quarter mile is a drag race. Okay, that's a standard drag race if you watch on like ESPN with the funny cars and the pro stocks. And the motorcycles. Those are quarter-mile races. And so it's going to do it in just 12 seconds. So assuming constant acceleration, how fast are we moving once it reaches the quarter mile? Okay, so let's write down our variables, right? So we know delta x, that is going to be 402 meters. Again, we don't care about the quarter mile, we just care about the meter measurement. If you're given how many feet or so were in a quarter mile, you would need to make this conversion. We're given the time, it does it in 12 seconds. Okay, we're given the initial velocity, which it tells us it starts from rest. And we're asked to find how fast is it moving at the end, right? And so we don't, the one that we're asked to not find is the acceleration, okay? We're not given it, we're not asked to find it. And if you remember the last equation, that's the equation we're going to use here. So we're going to do delta x equals v plus v0 over 2 times t. And now this is, we'll walk through this algebra because it seems a little, not difficult, but there's a lot more steps to it. So if we're looking for v0, actually we can get rid of v0. We're looking for v. So if we do a little simplifying before we solve, we're going to get vt, right, over 2. So this is what we're looking for. So the first step, multiply by 2, right? So we're going to get vt equals 2 delta x. And then we're going to divide this by t. And so it's going to give us a final velocity of 2 delta x over t. And then if you actually left that initial velocity, and you would have another step of subtracting v0 out. But again, for us, this is just 0, so we don't have to worry about it. And so we do v equals 2 times 402 divided by 12, because that's how long it took. All right, so 2 times 402 divided by 12 would give us 67 meters per second. Now, I know some of you guys are like, that's not fast, but if you convert that to miles per hour, it's about 150 miles per hour. Okay, now tell me that's not fast. Remember, your meters per second measurement will definitely be smaller than your miles per hour measurement. Okay, and then to convert make that conversion, you're going to do 3,600 over 1, and then 1 over 1609, okay, to get you to the miles. All right. Okay,